This is the Section 9.1 MathCast. It contains 3 lessons. Students are introduced to the chi-squared distribution as the sum of squared independent standard normal random variables, and their understanding of degrees of freedom is expanded to work with the chi-squared family of cumulative density functions. Students are introduced to and test a variety of chi-squared goodness of fit situations. In Lesson 9.1.1, the trash-get ball scenario continues, now with 3 hypothetical students wondering if any of their sample free throw percentages are significantly different. After trying to run 3 individual tests of proportion against their pooled proportion, they are seemingly inconclusive. They are instructed by their hypothetical teacher to try squaring and summing their individual z-scores for use with the chi-squared distribution. As confirmation of the chi-squared distribution's consistency with other tests, the technique of squaring and summing the z-scores is used on the same 2-sample test of proportion from the Math Notes box in Lesson 8.1.3, and identical p-values are confirmed. There is a Math Notes box describing the characteristics of chi-squared distributions. This is the student's first exposure to a family of cumulative density functions that's different depending on degrees of freedom. They will encounter this distinction between cumulative density functions of the same family again in Chapter 10 with standardized t-distributions. In Problem 9.3, Part A, one of the hypothetical students says, "We've been squaring and adding a lot of things in this class." You can remind the students that they have been squaring and adding statistics and data values multiple times before in Chapters 1 and 2 specifically. Problem 9.3, Part B continues the concept of degrees of freedom from several introductions and discussions found in Lessons 1.2.3, 1.3.2, and 2.1.4. The chi-squared distribution is the sum of squared independent standard normal random variables. Among the 3 contestants, there is a partial loss of independence because 2 statistics, or z-scores, are free to vary, while one must be fixed because they all share the same pooled proportion. Or, the alternate explanation of 3 z-scores, subtract the number of estimated parameters, being the pooled proportion, were used when finding the chi-squared test statistic. The rows and columns approach to finding degrees of freedom is explored in Lesson 9.2.1. In Lesson 9.1.2, students are prompted through a complete goodness of fit test, calculating the occurrence of first digits of a set of tree height data using Benford's law. Students are introduced to the formula for standardizing counts and the empirical requirement that all expected counts are at least 5, as they're prompted through an example of the chi-squared goodness of fit test. Problem 9.15 contains the discussion of degrees of freedom for the goodness of fit test. Again, there is a partial loss of independence in the individual contributions because the sum of the counts must be the same for both the observed and expected counts. Each category is free to vary except one that must fix the total frequencies, or the number of categories less the one shared estimate from the sample. Thus, the degrees of freedom are the number of categories less 1. There is a Math Notes box outlining all of the goodness of fit procedures in Lesson 9.1.3. Benford's law tends to stick in the minds of students to the point where they have trouble untying the terms chi-squared goodness of fit and Benford's law. Moving forward, make sure they know that Benford's law is just one of the many examples where the goodness of fit test may be applied, and that there is nothing about Benford's law that they need to memorize. There are many applications of the chi-squared goodness of fit test. Some of these can be hard to recognize by students. Lesson 913 is intended to provide practice in these multiple settings. Problem 921 introduces the concept of checking for uniformity among the counts. Circulate to check that students are not using Benford's law again. Problem 922 introduces ratio notation using 9331. A useful way to think about ratios in this situation is to notice that the ratios are equivalent to the following fractions, as students may find these easier to work with. Section 9.2 continues with the chi-squared test for independence and homogeneity.